Thank you for coming to this presentation on the new features in QC Ware Forge, the software as a service platform that's offered by QC Ware. I'm joined today by Sohum Thakkar, a quantum engineer at QC Ware. I'm Sean Weinberg, and I'm just going to be telling you a little bit about these new features. So just to review, for those of you who might not be familiar with QC Ware Forge, Forge is a software as a service platform which focuses primarily on quantum algorithms. Now, the algorithms that we focus are unique and performant quantum algorithms. We also offer hardware access, and we offer that hardware access through our partners. But I want to emphasize that we actually intentionally put algorithms in bold here because the primary focus of QC Ware Forge is quantum algorithms. There's a lot of outstanding services that are provided. There are a lot of outstanding services that you can find for hardware access, and we do provide hardware access through Forge, but the focus is on the algorithms. So with Forge, we actually separately target two different overall classes of users. These terms are not perfect, but they kind of get the idea across. The first type of user is a data scientist. This is someone that wants to use quantum algorithms, but they don't want to deal with a CNOT gate. They just want to know that, okay, I've got this problem. I know how I normally do this with, I don't know, scikit-learn or Gurobi or something like that. And I just want to run a quantum algorithm on it, but I don't want to deal with a quantum circuit. So for these users, we offer what we call turnkey algorithmic implementations. Turnkey is in you just turn the key in your car and it just turns on. The other type of user is the quantum engineer. So this just means anyone that actually wants to deal with quantum circuits directly and build their own custom quantum algorithms. For these users, we offer building blocks to construct quantum circuits. So essentially, we have algorithms, and those algorithms come with certain circuits, of course, and then we give you give some parameters and you get back a certain quantum circuit that you can then implement in your own workflow. Okay, so for data scientists, we offer algorithms in optimization, machine learning, and linear algebra. In optimization, we do quantum annealing and QAOA. For machine learning, we have algorithms for clustering, classification, and regression. In linear algebra, we have matrix multiplication and computation of distances. And finally, we have a new feature that I want to tell you about, which is Monte Carlo simulation, and specifically European option pricing. So it's some finance feature. For quantum engineers, we give circuits that are useful for input and output. This is data loading. So how do you convert classical data into a form that you can implement in a quantum algorithm? We also have tools for angles in QAOA, parameters in QAOA, if you do quantum optimization. And we offer kind of other techniques for manipulating quantum circuits and simulating quantum circuits, as well as translating between various languages like Qiskit, Cirq, Quasar. Now, I want to tell you about some new tools for quantum engineers. I mentioned that we have ways to do matrix multiplication with quantum algorithms. We're now offering the quantum circuit, so we're giving you access to the quantum circuits that we use for that matrix multiplication algorithm. Same thing for distance estimation. And one more thing, a fairly complicated term, NISQ amplitude estimation. I'm going to be talking a bit more about that later, but we're giving the quantum circuits for these for this algorithm. So just really quick, these are the backends that are offered through Forge. For annealing, we have D-Wave. For circuit model quantum computing, IonQ, Rigetti, and IBM. I should mention that the three on the left, D-Wave, IonQ, and Rigetti, are offered through AWS Braket. For IBM, you have to bring your own IBM credentials, actually. But I should mention that for the ones that go through AWS Braket, you don't need other credentials. You just use your Forge account. And we also have simulators, very performant simulators through CPU and GPU backends. So at a high level, this is what Forge looks like to a customer. It's someone that is just using quantum algorithms for binary optimization, linear algebra, machine learning, and now also Monte Carlo simulation. This is built on a stack. First, there's a sort of tool for translating into quantum circuits. And then we pass some of these circuits through Amazon Bracket. And finally, these are sent to our backends that I mentioned. So let's go ahead and get started getting into a bit more detail. I want to tell you about the linear algebra tools that we have for quantum engineers. So faster linear algebra is the name of the game here. When the point is that with the algorithms for linear algebra, the dimensionality of the data is key because the algorithms scale well with the dimension of the data. If you want to have a quantum speedup for linear algebra, the data has to be very high dimensional. And the reason that we're working on a linear algebra library is because linear algebra is fundamental to something like machine learning and obviously many other applications and optimization and so on. So currently, in linear algebra, we offer some API calls. Q dot, which is actually matrix multiplication. It stands for quantum dot product, but okay, we're kind of generalizing that. It's like matrix multiplication. We also have distance estimation, which computes Euclidean distance. Now, these functions were already in Forge. The new feature is that now we're giving you a way to access the quantum circuits that are used in the algorithms that Q dot and distance estimation run on. So Sohum is going to give a quick demonstration of this on Q dot circuits. So we're going to start by showing you just the sort of high-level turnkey implementation of Q dot. Then we're going to use this function, create Q dot circuit for quantum engineers to get the circuit. And then finally, once you have that circuit, then you can just implement that in whatever workflow you have.
Cool, thank you, Sean. So Q dot was already really intuitive for data scientists to use. And that's because, like all of Forge's machine learning and data science functionality, it was designed to be just like popular libraries like NumPy and sklearn. So here, when we want to use a quantum dot product, we can use Q dot in any place where we would use, for example, NumPy's dot product. So here, I'm just creating two very small two-dimensional vectors, and I'm going to compute the Q dot as well as the exact dot product. So here, I'm displaying them both, and you can see that there's a little bit of quantum error, and that's because it is actually running on a quantum simulator with 500 measurements. If you want to increase the accuracy of this, you would just increase the number of measurements. Here, I'm doing the same thing on length 100 vectors, and here I'm doing full matrix multiplication on a quantum computer. Very, very simple to use. Now for quantum engineers, we're actually going to give you the circuits that we use to do those calculations. So you start the same way. You produce some input. Here I'm producing some small length 4 vectors that we want to take the dot product of. So how do we actually get the circuit? Well, it's a really quick call to create Q dot circuit. And there we go. So if you measure this circuit, you should get the dot product between those two vectors. And of course, with Forge, it just takes one line to translate to Qiskit or any of the other supported languages, as you can see here. Simple enough. Back to you, Sean.
Thanks. Yeah, so as you saw, we have this functionality for linear algebra. The one that Sohum showed you was for matrix multiplication or dot products, but we also have a similar one for distance estimation. It's the same story. And the point is that no one's going to come to get into quantum computing just to do matrix multiplication probably, but the point is that that's part of a larger workflow. And we're now giving you the tools to customize the way that you use a quantum algorithm for something like matrix multiplication or other linear algebra functionality, and then implement that into whatever you're already, whatever problem you're already solving. So closely related to linear algebra is the concept of loading data. Arguably, we should have done this before linear algebra. So loading data is something you may have heard us talking about before. Can you go to the next? Yeah, so the idea is how are we going to take classical information, classical just numbers like a vector, and then convert that into a quantum state. There are many different approaches to that. There's lots of theoretical questions about what that even means. In this case, we're taking it to mean something pretty specific, and Sohum is going to show you in a demo what we mean. But what I want to emphasize now is how important loading data is, because if you're going to do any calculation on classical information with a quantum algorithm, you first need to load the data. So having a better approach to loading data means that there's more information to run your algorithm on. But it doesn't just mean that you have more information. Better loading also means faster algorithms. Because, as I mentioned, the algorithms that we have scale, the speed up scales with the dimension of the data. So this is very important, and that applies to lots of quantum machine learning algorithms, for example, where the speed up is proportional to the number of features, for example. So here's a quick demonstration on how we load data in Forge. First, we're going to prepare a data set. Then we're going to create a quantum circuit which loads the data. That's why it's a quantum engineer targeted thing here, because we first start with some classical data, then we get a quantum circuit that converts that data to a quantum state, and finally, we're going to measure that quantum state to retrieve the original data to show you that it was there in the first place.
Sounds good. All right, so first step in loading data is preparing some data. So let's create some classical data. It's some abstract art, up to you to interpret. And all we need to do to create a circuit to load this data is use this functionality, which is loader. And there we go. So this is a pretty deep circuit because it's a 30-dimensional data point. But it does fit, because of our optimized loader, it does fit in 11 qubits, which happens to be the size of IonQ's public machine. So let's do this. Let's run a simulation and see if we can kind of pull it back from that simulation. So it's really simple to do this, because not only do we give you the loader circuit, but we also give you exactly where that data went into the state vector after you finish running the circuit. And okay, so that was a pretty deep circuit, as you saw. But we also, it's very simple to run on hardware, on Forge as well. So here I'm doing the exact same thing. I'm actually creating a little bit of data, which is just 1, 2, 3, 4. It's just a vector. And we're gonna load it into actual hardware. And so we ran this a little bit before. And so as you can see, this is the simulation, and this is the actual hardware run. So the simulation is kind of perfect, as you say, and the hardware actually gets very close with this. So we invite you to experiment and load as large data as you want. All of these notebooks are available in Forge. Thanks, Sean.
Okay, so the point here really is that, like I mentioned, what we're talking about here is a tool which is positioned for a quantum engineer. So you should really be thinking about, if you are building quantum algorithms yourself, but you don't want to deal with the pain point of converting classical information into a quantum state to then use in your algorithm, Forge can help you with that particular pain point. And it's quite easy to do so. Okay, so now we're going to get more into data science, but we're going to extend data science to mean quant, I guess. So derivative pricing. Probably not what you expected to hear about. So we have some new algorithms that you can read about in these papers, which have application for pricing financial derivatives, so options. Specifically European options. So it's a starting point. But the algorithm that we have is more general than just finding its application in finance, but that is the application that I will be highlighting today, because we have some functions in Forge that are specifically for that application. So this was research that we did in collaboration with Goldman Sachs and IonQ. We developed this algorithm called NISQ amplitude estimation. It's related to amplitude estimation, but as it sounds, NISQ, it's a more low depth variant. But even though it's low depth, it still gets good results. To that point, Standard amplitude estimation algorithms, the problem with them right now is just that the number of years of hardware progress before they'll be viable is a bit much. The variant of amplitude estimation that we have, NISQ amplitude estimation, it does come with slightly less of a speed up, but it comes with a substantially less steep quantum circuit, which means that there's less hardware requirement. And what that translates to is fewer years of wait until there's a commercially viable application with it. So here's a demonstration that Sohum will give on how we use this. And it's just going to be pricing a derivative. So it's going to be pricing a European call option specifically. The first step is going to be to define parameters for the European call. So these are going to be sort of financial parameters. Then we're going to price the option with classical simulation, and that's going to take many runs to do. And then we're going to price the option using a quantum simulation of NISQ amplitude estimation, and that is going to take fewer runs, and fewer runs translates to less weight once hardware evolves.
Thank you, Sean. So as Sean mentioned, the first thing to do for pricing an option is to define the parameters. So here we're creating a European option, and we're using this helper class called European option. It's actually available on Forge for you to poke through. Essentially what it's going to do is just define the circuits for pricing and calculating the payoff of a derivative. So I'm doing that. And here we're going to run the exact model. So we're going to figure out what the actual price of the derivative is. And the goal is to come very close to this price, but with way fewer runs of the model. So here the price is about 1.944. And in order to price this without amplitude estimation, what you would need is on the order of 1 over epsilon squared runs, which epsilon is your precision parameter. So this would need around 40,000 runs for about 99.5% accuracy. So keep that number in mind, 40,000. So with NISQ amplitude estimation, what you can do is kind of tune the algorithm to how deep you want the circuit to go. And the depth of the circuit is kind of how near-term the hardware is. So on kind of near-term hardware, let's run this algorithm and see, this is on a simulator, and see how many runs it actually takes. So we got pretty close. So the result was 1.941. So that's within 0.005 accuracy. And it only took 26,000 runs. So this is on short-term hardware, but we already see that this is actually resulting in fewer runs. But on longer-term hardware, the results can get even better. So here we got the same price, same accuracy, but we actually only took 5,000 runs. So that's a huge speed up over classical. And what you would expect is if you want to get closer to the real answer, this difference gets significantly larger. All right, thanks.
That was great. Thank you, Sohum. So as you can see, when you use NISQ amplitude estimation, the difference is that you don't have to do as many runs. So once you get to the point the hardware is at a more advanced state, that would translate to just waiting longer for the price of the derivative. Sorry, waiting less long for the price of the derivative. Okay, so that was the quants or the data scientists' version of amplitude estimation. Now the quantum engineers version is of course a bit more requires a little bit of technical language. So we have some new API calls. The first API call, make schedule. So you're going to ask me, what is a schedule? What on earth is that? So NISQ amplitude estimation, which is the algorithm that you just saw for pricing the option, uses something called a schedule. And a schedule simply means it's sort of an iterative plan of how many times you're going to run a circuit at various circuit depths. And this is just a step that you need to do in order to run this algorithm. So the first step is to call this function makeSchedule to make a schedule. Then we have functions to run that schedule. Then once you get the result from the algorithm, you have to post-process that result with maximum likelihood estimation. So here's a demonstration of that. It's kind of an obvious list of things. We're going to prepare a circuit. Now that circuit, this is important actually. You earlier saw a demonstration with a call option, but actually this algorithm applies to more general circuits. So this circuit that Sohum is going to use is actually going to be back from the Q dot, the matrix multiplication circuit. Once we prepare that circuit, we're going to make a schedule for it. We're going to run the schedule, and then we're going to look at the results.
All right, let's do it. So back from the create Q dot demonstration, we have the same setup. So we're going to create 2 length 4 vectors, and then also produce the circuit that takes the dot product of these 2 vectors. And the goal here is to approximate or get very close to the actual dot product of this circuit with way fewer runs. So here, because we're not having all of this handled by that helper class European option, we're going to have to do this ourselves. So here we're making a schedule, as Sean explained to you. It's a crucial step in the algorithm. And then we're going to run the schedule. And we're running this on a simulator. And when we process the results, we should get pretty close to the exact dot product. So yes, we got very, very close. Can't actually see it from here, but it's got a few zeros in front of it. The cool thing about this is that we can actually run the same thing on hardware, and it's absolutely seamless on Forge. So let's go ahead and do this. So we ran this hardware run just before hopping on stage. And as you can see, we get the same, we get very, very close. It's a little bit farther than the simulation run, but that's just the state of hardware. But it's cool to see that even today, you can use NISQ amplitude estimation to get a faster result. Thanks.
Great. Thank you. So that shows you how you can use this same NISQ amplitude estimation algorithm in a more general context than what we showed you earlier. So if you are someone who considers yourself a quantum engineer or similar, or you work on a team with such folks, they may be able to use our NISQ amplitude estimation framework to develop some new approaches for something that is not what we thought of. Okay, so those are the new features that I wanted to highlight. Now, let me tell you just a little bit about things that are more down the road that are on our roadmap. So in machine learning, we are planning to introduce quantum neural networks on Forge, as well as feature selection. And I should mention, by the way, that one distinguishing feature about the quantum neural networks that we're going to be having on Forge is that they have kind of provable guarantees. That's sort of the type of neural network that we're really interested in. In optimization, we're going to be introducing functionality for mixed integer programming, so going beyond binary optimization, as well as decomposition to take larger problems and break them into smaller problems. In linear algebra, we are going to be introducing some dimensionality reduction techniques. And in chemistry simulation, we're going to give you some tools to compute interaction energies between molecules. For quantum engineers, the roadmap items for input and output, so for loading, we're going to introduce a new type of loader, a subspace loader, also known as a Clifford loader. In machine learning, some similar to what I said before, quantum neural networks, but this time exposed at the circuit level. And at linear algebra, again, dimensionality reduction, but exposed to the circuit level. Okay, so those are the new features, so those are the new features and then the roadmap items. So if you want to use Forge, if you haven't tried it, you can try it out for free. We have a developer plan, which is basically a free trial. You get unlimited CPU time. You do get some hardware and GPU time, 1 minute. And one thing I should mention is that in this plan, there are some restrictions on some of the functionalities. So you have access to the kind of data scientist functions, but not all of the quantum circuit functions. For paid plans, we call them enterprise plans. There's several different levels, but of course there's unlimited CPU time, and then you can purchase a certain amount of access to hardware time. And there's multiple user seats. So that's just about everything. Thanks for listening. Yes.
So I'm going to use some classical language, not completely required, but there's a great temptation when you have all these backends to benchmark them against one another. And if I treat Forge as a compiler, I write a program in your language, Python, the language you have. I compile for each platform, I run each platform, and I look at the results. But how do I know that the results reflect the innate properties of the platform versus your ability to compile for an optimal way for each specific platform? Are you depending on the vendors to provide a intermediate representation that they qualify as being the best way to the platform, or are you doing something?
Yeah, that's a great question. So because Forge is something which is very high level, and then when you run an API call in Forge, first it goes through the API, right? Then if it's some algorithm, then you have to trust our implementation of that, which we write in some circuit model language, and then that will then get sent to the hardware provider, and then we have to trust that they're doing things in a reasonable fashion. So there's many layers before we get to the final step of compiling the instructions to send to the hardware. So I would say that if the goal is to kind of do a comparison, let's say you want to do a comparison between the performance of, I don't know, let's say Rigetti's hardware and IonQ's hardware, then I would actually not recommend using Forge for that purpose, because Forge is really meant for someone that wants to essentially implement some quantum algorithm, and that's their primary interest. It is not really a benchmarking tool. And when you switch from one backend to another, there's too many things that you have to trust along the way, which is what you were alluding to, for that to be a very scientific comparison. So if you want to do that kind of direct benchmarking, it would probably be better to work with those vendors in a very direct sense. Whereas in Forge, the convenience is that what you can do is you can say, okay, I have this algorithm that I want to run. Let's say QAOA, for example, and you tried running QAOA on Forge and you got a certain result, and you say, okay, I've heard that an ion trap computer has all-to-all connectivity, and I feel like my problem might benefit from that. You can switch to IonQ then with just changing a backend string, and then get that result, and then see whether or not it's better. Now, is that as scientific as working as directly with the vendor as possible? No, because you don't know all of the steps along the way. But if you get a much better result when you use the IonQ backend, that is a very simple way to swap backends, just changing a string.
When you started out talking about data science, you said that you were giving them the ability to ignore the circuits and the back-end mechanisms. And it sounds like you're just kind of back off of that, because there are going to be people like data scientists who write once and run everything. And now kind of denying they have to translate for each individual platform. Therefore, they have to learn a lot more to be able to carry out that control.
Well, so the benefit when you use Forge is that you specify the problem once, and then you just select which backend you want when you're using Forge. So I would presume that most data scientists would prefer to do it that way than having to learn a different language for every backend.
Oh, understood. Yes, absolutely. And for the data science functionality, we do optimize in some cases. So like when we expect something to actually be performant, for example, in QDOT, we do some optimization on the back end as well. But for the quantum engineer functionality, we don't.
Yeah, that's important actually. The data science functions, we take every liberty to write the algorithm in the most optimal way that we see fit for the specific backend.
And we do have the power to, optimize this as we see fit.
Any other questions? Okay.
All right, thank you.